Black holes are the most iconic things in our universe. Their mind-bending properties were debated for generations and were pondered by some of the greatest minds of our time. Today, we know that black holes are real, and as a result we can begin asking the next big questions. What lies beyond them? How do they die? And most of all, what is the biggest black hole in the universe? Well, it's likely that TON 618 is up there with the biggest, if not the biggest, in the universe, and while we don't know much about it, its profile is truly magnificent. This radio-loud and hyperluminous quasar was once thought to be just another star, but we now know that this monster's photonic relay is emanating and calling us from much further across space, over 10 billion light-years into the void. But is this beacon of the cosmos really what we think it is? With so many properties that push the limits of our understanding on black holes, TON 618 may have another explanation. But until we find that, we must assume that this record-breaking beast is the largest and most massive black hole in the entire known universe. TON 618 is the catalogue title of a quasar located at the centre of a galaxy approximately 10.37 billion light-years from the Earth, in the constellation of Canes Venatici, near the galactic North Pole. Despite this unfathomable distance, it shines with an absolute visual magnitude of -30.7. This number equates to the brightness of over 140 trillion suns, making it one of the brightest objects in the known universe. We will cover more about why this is in a moment, but in a quasar, the mass of the black hole usually indirectly corresponds to the amount of light it produces, and as such numerous calculations have estimated the mass of this engine black hole to be over 66 billion times the mass of our home star. This mass is both hard to visualise and hard to fully appreciate, but for some sort of perspective, the Milky Way's central black hole is approximately 4.3 million times more massive than the Sun. Sagittarius A is largely responsible for anchoring our entire galaxy together, which could be up to 200,000 light-years in diameter. Yet its mass doesn't equal 1,000th of the total mass of TON 618. Thanks to our study of black holes, we can use what we already know about its mass to estimate its actual size, and the results will truly blow your mind. If our calculations are correct, then the radius of its event horizon, the boundary beyond which nothing can escape including light which gives it the distinctive black colour, will be approximately 194 billion kilometres. This radius dwarfs even our entire solar system, and then some. The solar system's diameter is a little under 300 billion kilometres, whereas TON 618's event horizon diameter is close to 400 billion kilometres. But then, how is this black hole so massive if the emissions we see are from billions of years ago, when the universe was significantly younger? The universe is about 13.8 billion years old, and this likely formed between 1 and 2 billion years after the Big Bang, meaning it could have been as young as 1 billion years or less when the light reaching us now began its intergalactic journey. This is very young for a black hole, and yet the signals are indicating that a black hole this young is larger than anything we've been able to find in the universe billions of years on. After all this time, there's no telling how big it has become, but there are a few ideas on how it might have come to be so large at such a young age. The main theory is that this black hole was a direct collapse black hole. Instead of being formed by a dying star's supernova, this black hole was formed by a supermassive gas cloud collapsing under its own gravity. This process can also take all the stars within the gas cloud with it, rapidly consuming thousands more distinct sources of mass. This process would generate an inconceivably large supermassive black hole, and is the expected way in which most engine black holes at the centre of galaxies formed. In the future, we may re-estimate the black hole's measurements and come up with new figures, but for now, these are the facts. But what about its history? How was this black hole discovered, and when did we realise that it was the most massive we had ever found? TON 618 was first noted in a survey of faint blue and white dwarf stars around the Milky Way's galactic plane in 1957. Back then, it was mistaken for another blue star, and was listed as the 618th member of the Tonat-Zintla catalogue of globular star clusters, thus coining its name. However, moving into the 1960s, astronomers started noticing radio-loud sources of light which appeared similar to stars, but the source of this radio energy was unknown, and thus the term quasars and X-ray photographs indicated that these radio-loud sources were emitting from the centres of distant galaxies, and the light reaching us from these quasars is billions of years old. But how does a black hole, scientifically the darkest thing in the universe, even shine in the first place, let alone shine brighter than the stars a millionth of a percent of the distance away? Well, the process begins with the immense gravity of central galactic black holes. When gas and matter orbit the black hole, they orbit the area at immense speeds, as do the light and energy released when they consume things. When a black hole destroys something, it does through the trivially named process of spaghettification. As you get closer to the singularity or centre of the black hole, the gravity becomes so exponential in its increase that even a difference of a few million kilometres can lead to vastly different levels of pull on the object, essentially shredding up whatever it is. The gases from this shredded matter form a disk around the event horizon of the black hole and can orbit it, forming an accretion disk. When this disk orbits, it swirls at unimaginably fast speeds, and the friction generated releases unbelievable amounts of heat. The accretion disk can also cause black holes to emit plumes of plasma, known as relativistic jets. These jets travel away from the black hole at nearly the speed of light, and this and the accretion disk shine so brightly together that the light we can observe drowns out the surrounding galaxy. When it does this, we call these illuminated black holes active galactic nuclei. A sufficiently luminous active galactic nuclei is classed as a quasar. With our growing understanding of quasars, the hunt was on for more, and before long a radio survey implemented the spectral data from the object. She detected the spectral emission lines, the lines in surrounding